All right, so let's go ahead and get started on Pset 2. So let's get my pen ready to go. Not here, I want to draw. All right, for A through C, identify what conventional unit cell is present. So let's go ahead and do that. So we have simple cubic for A, we have FCC here, and we have BCC here. Number of atoms in each cell, 1, 4, 2. Number of nearest neighbors, 6, 12, 8. The nearest neighbor distance is 2r here, 2r here, 2r here. Excellent. The lattice parameter for simple cubic it still is 2r. For FCC, it's 2 square root 2r. And for here, we have 4r divided by square root of 3 for our lattice parameter, which is a. Let's see, the lattice parameter. The next nearest neighbor distance is the lattice parameter, except for here, which is going to be 2r square root of 2. And the atomic packing factor, less than 0.74 for this guy and this guy, but for FCC, it's going to be 0.74. Are any of these cells close packed? Yes, FCC is close packed indeed. And are any of these cells primitive unit cells? Simple cubic is our primitive unit cell. All right. That was quick, but I'm going to erase this now. So let's determine let's see, and that's a little typo here. Determine the crystallographic directions. So in A, and then basically, are there any directions that are close packed in A? So that's a little typo. We'll make sure to make a note of that. So let's look at here. So here, again, finish minus start. So our finish, I'll do the first one. Finish is 0, 0, 1. And then minus, where do we go? 1, 0, 1. So where are we going? So it's going to be 1 hat. Let me tighten that up a little bit. So 1 hat, 0, 0. And there we go. So that's that first direction here. Let's look at this direction now. So again, finish is going to be at 1, 0, 0 minus the start, which is going to be at 0, 1, 1. So we are going to have 1 hat here. So there we go across there. Let's look at this guy next. So our finish again is going to be 1, 1, 0 minus my start, which is at basically 0, 1, 1 half. So that is going to end up being 1 hat, 1 hat, 0, 1 half hat. So I need to multiply that out. So it's going to be 2 hat, 0, 1 hat. Or 2 hat, 0, 1 hat. There we go. And then finally, actually no, it's the last little one here. This guy. So where do I finish? At half, 0, 0. Where do I start at? That is going to be at basically an x of 1. I'm going to call that half, and then 1 half, 0. So I'm left with 1 half hat, 1 half hat, 0. So 1 hat, 0. There we go. And that's all we've got right here. So that's for your directions. Are any directions close packed in A? Yes. So this direction in A is close packed because that is part of the basically 1, 1, 1, 0, 0. That is our close packed directions in simple cubic. Fantastic. For B and C, identify the planes, indicate the origin. Are there any planes that are close packed? Indicate the post. So for A and C, A, there are no close packed planes. C, there are no close packed planes. For FCC, 1, 1, 1 is only our close packed planes. So for B, I'm going to choose a new origin. I'm going to choose it over here. So my intercept is going to be at -1, so my plane is 1 hat, 0, 0. I'm going to keep my origin here. My intercepts are going to be 1 half, 0, or infinity. So my plane is going to be 2, 2, 2, 2, 0. Identify planes, indicate origin. Are the planes close packed? No, they are not. Again, just from what we just talked about previously. Calculate the planar density quantitatively in in our plane in B. So in our plane in B, we can see I have atoms here, 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 and here. So what is my planar density equation? It's going to be number of atoms, fourth, plus 1 in the center. So that's going to be 2 times pi r squared divided by the area of the plane, which, remember, this area is 2r square root 2. So basically 2r square root 2 squared, a squared. Let's pull out the old, this should be less than our magic number of 0.9069. So basically 2 times pi times r squared. I'm going to divide that by 2 times r times square root of 2 squared. And let's look at that numerically. And not close packed, not a magic number, and we are good to go. Fantastic. All right, 5. Draw an FCC cell in D. So FCC, the hardest one to draw, of course. Boom, boom, top, side, front. There we go. There's my FCC. Draw the 2, 0, 3 direction. Again, whenever we're drawing, we have to stay within the plane. So now the drawing skills come into play. My worst set of skills. So I need to make sure, so I'm going to do a finish minus a start. Here, minus that here. So I'm going to do, basically I need to do a 2/3, and then, these are always confusing, but I'm just going to do, a 1 and a 1 here, because I'll subtract those. And now I need to do something where if I multiply by 3, so actually I could do 0 and 1, and then I could do, multiply by 3, I need, I could do 1/3 and 1. So that'll leave me with, for example, 2/3 hat, 0, 1 hat. Multiply that by 3, and that will give me 2 hat, 0, 3. So I can draw that. My finish is going to be 1/3, 1/3 and 1, 0. So that'll be where the arrow is at. And then, 1, 1, 1. So right here, so it's going to be here to just right here. And there we go. That's it. That's the direction. Draw the 1, 1, 1, 1 minus 1 plane. So I'm going to have to change my origin because I need to go down. So I'm going to do my origin like this. So this is my new origin. So I'm going to go here. I'm going to touch one here. I'm going to touch here. And then I'm going to touch down here. So it's going to go boop, boop, boop. And there we go. That'll work as well. Calculate planar density of the plane quantitatively. Is it close packed? Yes, that is a close packed plane. And we can prove that. And it's already done in our notes, actually. Great. Draw the following directions within the unit cell below, 1, 1, 2, and they must be contained in the unit cells demonstrated in class. So I'm going to actually write these 1, 1, 2, 1, 3, hat, 0, and then I'm going to do 1, 1, hat, 3. All right, so let's go with 1, 1, 2 first. So kind of the same procedure as last time. So I want to do, for example, a half, and then I'm going to do basically a 0, finish, minus my start, which is going to be, actually, I'm going to roll that up here, which we'll just do, how about 0, 0, 1, and that should do it for me. Actually, I need to switch this. Actually, I need this to be a 1. You could do that at the origin, but that's a little bit boring. I'm going to do this as a, I don't want it as a 2. I'm going to do this a little bit more exciting. So 1, 1, I'm going to do this a half, and then I'm going to make this 1, and this is 0. So I could do, this is going to be my finish, arrow here, and my start is going to be a half like this. And that should give me what I want, and it does indeed. So it's just going to go like this. Excellent. So that one will work. What about this one right here? Let's do the same kind of procedure here. So I'm going to keep this as, actually I need to make this because we're going to do 3. So this needs to be, for example, 2/3, 1/3. This needs to be a 0 and a 1. This could be a 1 and a 1. And that should work. Yes, it will. So my finish is going to be 2/3, 0, 1. So it's going to be my arrow somewhere here. And my start is going to be 1/3, 1, 1. So like this. There we go. And then 1 hat, 1 hat, 3. We could do something very similar actually to modify this. So I'm just going to keep 2/3. Actually, because I need this, yeah. 2/3, 2/3. Except I'm going to make this 1/3. 1/3, 1/3, 2/3, 2/3, and then 1, 0. So again, very similar. So 1/3, 1/3. So 1/3, 1/3, like 1 up here. That's my finish. And you get the picture. 2/3, 2/3, 0. So it's going to go like this up here. And there it is. There you go. All right. Now draw these planes. So 1, 2, 1, or actually -1, -1. So I'm going to need to go. Let's see, what would be a good one to be here? So I think the easiest one would be to do the following. If I choose this origin, because I can go, actually the best origin would be right here. So I'm going to go this origin, choose this origin. So my intercepts here are -1 here. So that's going to be 1. It's going to be basically a half in this direction. So it's going to be right here. And then it's going to be -1 right here. So it's going to be toot, toot, toot. This little guy right there. Excellent. And we could keep, actually we'll change it a little bit. So for example, I want to go, actually we'll keep it. Because I can go here, actually. Nope, I want to do a little bit different. So I want to go, let's do it right here. Doesn't need to be in the top, but just for example. So I can go 1 here. I can go, actually let's move it back here. So I could go 1 here. I could do -1/2 here, and that's it. And then you could do the same thing on the bottom here. So it'd be 1, this, 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 and there we go. Fantastic. All right, we're at the last problem. So take a look at PDF already below. Materials this. What must be integral in the first peak? What would the second integral? What would the second integral under the peak look like? So when we're looking at RDF PDF, I know it's a metal, so I know my nearest neighbor distance must be equal to 2r, and this is either 2r square root of 2, which means it's either FCC or simple cubic, or this ratio has to be 4r over square root of 3. So, for example, I'm going to do Mathematica. If I could pull it up. Let's pull up Mathematica. All right. So I'm going to say, for example, A FCC is equal to 2 times r times square root of 2. A BCC equals 4 times r times, or divided by square root of 3. If I do basically A FCC divided by 2r, I'll get this number. Let's get this ratio. If it's BCC, I get this ratio. So what is the ratio that we have? Because we're given both. 3.85 divided by 2.72. 1.4. So it seems like it's either FCC or it's simple cubic. So it's not a BCC structure. So now I also know that 2.72 divided by 2, so 1.36, and it has to be FCC or it has to be simple cubic. So now I could just go into my periodic table and I could look at my, it's a metal, so I need to look for my metallic radii, and my metallic radii is the second number there. I could see here the structure, so it must be FCC. So it's got to have the dot, or it just has to be cubic. So I'm looking for dots. So, and it has to be 1.36 metallic radii. And here's where the searching begins. PD is pretty close. 1.36, 1.36. Let's look for you, my friend. 1.36. We can look on the other side. 1.36, but we need the dot, remember. Iridium. There we go. That works. So iridium is a possible solution. And with that, that is your Pset 2 solved and ready to go. Thanks. We will see you next time on Pset 3. Have a great day. Bye.